Hello everyone. I hope that all of you are fine and enjoying good health. Welcome to another lecture of robotics and automation. In the previous lecture, we talked about automation, its types and advantages. In today's lecture, we shall talk about programmable logic controllers, and later we shall also study about how to program PLCs or programmable logic controllers using the ladder logic. So let's begin. In digital electronic systems, there are three basic kinds of devices: memory, microprocessors, and logic. Memory devices store random information such as the contents of the spreadsheet or database. Microprocessors execute software instructions to perform a wide variety of tasks such as running a word processing program or video game. On the other hand, logic devices provide specific functions including device-to-device interfacing, data communication, signal processing, data display, timing and control operations, and almost every other function a system must perform. The advent of a PLC began in 1970s and has become the most common choice for manufacturing controls. So nowadays PLCs are quite common, and they started in 1970s, and nowadays in automated industry you will find them quite common. So what is a PLC? A programmable logic controller, also called a PLC or a programmable controller, is a computer type device used to control equipment in an industrial facility. So it's like a computer, type of computer you can say, but it's specific to the to control the industrial devices. The kinds of equipment that PLCs can control include conveyor systems, food processing machinery, auto assembly lines, etc. PLCs are often defined as miniature industrial computers that contain hardware and software used to perform control functions. So PLCs are just similar to computers, and they have a hardware. For example, here you can see this is a PLC here, and this PLC is used to control different devices in the industry. So a PLC has a hardware, it means it has some kind of memory, a processor, and then logic devices to interface the inputs and outputs. And then so you can control, in industry you have different motors, sometimes DC motors, AC motors. You have to control them. You have to turn off alarm or some pneumatic devices. So this here actually this is the, I would say, more like a laboratory version of a PLC where the students can perform experiments. But in industry it might not look like this messy setup. It will be like more professionally arranged wires, but in lab environment you want, actually students want more flexibility to test the functionality of the PLC. Unlike general purpose computers, the PLC is designed for multiple inputs and outputs arrangements. Extended temperature ranges, immunity to electrical noise, and resistance to vibration and impact. So in short, PLC is more designed for practical industrial environment. It's like a small computer which has more like interfaces, user interfaces, but it is very It can work in very harsh environments. Okay. National Electrical Manufacturers Association has defined PLC as a digitally operating electronic apparatus which uses a programmable memory for the internal storage of instructions for implementing specific functions such as logic, sequencing, timing, counting, arithmetic to control through digital or analog input-output modules, various types of machines or processes. In a traditional industrial control system, all control devices are wired directly to each other according to how the system is supposed to operate. In a PLC system, however, the PLC replaces the wiring between the devices. Thus, instead of being wired directly into each other, all equipment is wired to the PLC. Then the control program inside the PLC provides the wiring connection between the devices. The control program is the computer program stored in the PLC memory that tells the PLC what's supposed to be going on in the system. So PLC actually, instead of directly connecting the devices, for example buttons to the motors, so what they do in a PLC system, what they do, they actually connect the button to turn on the motor, but there is PLC in between. Okay, and the reason is that it may provide more functionality. For example, it can also provide more safety functions to this motor control, maybe some speed functions or timing functions, how long the motor will remain on. Instead of just connecting the button with the motor to turn it on off, a PLC will give you much more functionality instead of just turning on and off. The use of a PLC to provide the wiring connections between system devices is called soft wiring. For example, let's assume that a push button is supposed to control the operation of a motor. In a traditional control system, the push button would be wired directly to the motor. In a PLC system, however, both the push button and the motor would be wired to a PLC instead. Then the PLC's control program would complete the electrical circuit between the two, allowing the button to control the motor. So this is same as we have here described already. And so what's the, if we want to draw it here, so let's say in a traditional system we have here a button. So this is a button we have here. This is a, let's say, on off button, and this is connected to a motor, a DC motor, let's say. So this is a traditional system. So this is a traditional system where the motor is connected to directly to the button where you can on or off this motor. Okay, but in a PLC system you have something like this. You have a button here, on, off button, and then you have here a PLC, and then you have motor here. So This is, we call it PLC system. So this is the difference between the traditional system and a PLC system. Okay, so another advantage of using PLC system as compared to traditional system is that you can use components for multiple purposes. For example, here if you hardwire this button with this DC motor, and so it's hardwired, you cannot really change its function. Okay, let's imagine if you have multiple motors or some other devices, and so since your switch is directly and connected with the motor and it's fixed connection, so you cannot use it for multiple purposes. But in case of PLC, the components can be used for multiple purposes. For example, if you have 2 or 3 motors, and this button can also be used for multiple motors to turn them on and off, and you can program them, so which motor actually you want to control using this button. Okay, so this is again an advantage of using the PLC system. Okay, so now let's see what are some components of the PLC. A PLC consists of 2 basic sections: the central processing unit, which is the CPU, and the input-output interface system. The CPU, which controls all PLC activity, can further be broken down into processor and memory system. The input-output system is physically connected to field devices like switches, sensors, and provides the interface between the CPU and the information providers like inputs and controllable devices, which are outputs. So basically it's just like a computer where you have some inputs, outputs, and then you have also some processing unit where you have microprocessor, and then you have memory. To operate the CPU reads input data from connected field devices through the use of its input interfaces, and then executes or performs a control program that has been stored in its memory system. Programs are typically created in ladder logic, a language that closely resembles a relay-based wiring schematic, and are entered into the CPU's memory prior to operation. So PLCs are programmed with ladder logic. This is a programming language for PLCs, and its origin it looks like relay-based wiring. In the relay you have some contact points, and these contact points change according to the on-off sequence. So same terminology, same logic is being used in this ladder logic programming language to program PLCs. Finally, based on the program, the PLC writes or updates output devices via the output interfaces. This process, also known as scanning, typically continues in the same sequence without interruption and changes only when the change is made to the control program. The schematic diagram of PLC is shown in figure below. The basic components of PLC are, so The first one is input module, then we have output module, and then you have a processor, memory, power supply, and programming device. So in this figure you can see that how they are interconnected, starting from inputs from sensors or switches. You get the input from using the input module, and then you also have some outputs from where you can give output to the motors or other actuators. And then there is some kind of interface that connects the input output to your CPU. Inside the CPU you have a microprocessor, same like you have microprocessor in your smartphone or computer, and then you have memory, the RAM, or also it could be ROM memory also. And then there's a power supply, and then a detachable programming device by which you can program your PLC. So let's see in detail about some of these components. Let's start with the input-output module. The input-output module is a connections to the industrial processes that are to be controlled. If the CPU can be thought of as a brain of the PLC, then the I/O system can be thought of as arms and legs. The I/O system is what actually physically carries out the control commands from the program stored in the PLC's memory. The input-output system consists of two main parts: the rack, I/O modules. The rack is an enclosure with slots in it that is connected to the CPU. Input-output units are the interfaces between the internal PLC systems and the external processes to be monitored and controlled. Input-output modules are devices with connections terminals to which the field devices are wired. Together the rack and the input-output modules form the interface between the field devices and the PLC. When set up properly, each input-output module is both securely wired to its corresponding field devices and securely installed in a slot in the rack. This creates the physical connection between the field equipment and the PLC. All the field devices connected to the PLC can be classified in one of two categories: inputs or outputs. Inputs are devices that supply a signal data to a PLC. Typical examples of inputs are push buttons, limit sensors, switches, and measurement devices. Outputs are devices that await a signal data from the PLC to perform their control functions. Lights, horns, motors, and valves are all good examples of output devices. For example, a bulb and its corresponding wall switch are good examples of everyday input and outputs. The wall switch is an input which provides a signal for the light to turn. The bulb is an output which waits until the switch sends a signal before it turns on. Let us assume a bulb switch circuit that contains a PLC. In this situation, both the switch and the bulb will be wired to the PLC instead of each other. Thus, when the switch is turned on, the switch will send its turn on signal to the PLC instead of the bulb. The PLC will then relay this signal to the bulb, which will then turn on. Okay, so our second part is the central processing unit. The central processing unit, or the CPU, is the part of the programmable controller that retrieves, decodes, stores, and processes information. So you have to get the information, you have to decode it if it's already coded, and sometimes you have to also store the information, and finally the main purpose is to process the information. Logic, sometimes it's logical additions, and sometimes it's just shifting the some information from one register to other. It also executes the control program stored in PLC's memory. In essence, the CPU is the brains of the programmable controller. It functions much the same way as the CPU of the regular computer does, except that it uses special instructions and coding to perform its functions. The CPU has three parts. Number one is the processor, and then the memory system, and then the power supply. The processor is the section of the CPU that codes, decodes, and computes data. The memory system is the section of the CPU that stores both the control program and the data from the equipment connected to the PLC. Memory in a PLC system is divided into program memory, which is usually stored in EPROM or ROM. This is the permanent memory, and the operating memory, the RAM. The RAM memory is necessary for operation of the program and the temporary storage of input and output data. And then you have the power supply. It is a section that provides the PLC with the voltage and current it needs to operate. So this is also important. A stable voltage is also important for proper working of a processor and the whole PLC. And then there is a programming device, as you have seen in the figure. This one here, and this is detachable. Actually, if you see it in this, in the previous section, you also have seen this programming device. So the PLC is programmed by means of programming device. The programming device is usually detachable from the PLC cabinet so that it can be shared between different controllers. So usually you need one programming device, and this can be actually shared with multiple controllers. So here, so this, I guess here, this one is the programming device we have. It can be used for programming of multiple PLCs. You just need to connect them. Okay, so now we know the major components of the PLC, and now we shall see how a PLC works. A PLC works by continually scanning a program. It consists of three steps: check input status, and then execute the program, update output status. So these three steps, it continuously keep doing. So this is like a loop where first step is to check the input status, okay, read the sensors and the switches, and then whatever the program is written in your memory, the processor will execute this program, okay, process the information of the program and the inputs, and then it will write some data on the outputs, or update the outputs, okay, update output status, and then this process will be continuously repeated forever. It will be like, this is like a scanning from top to bottom, and then top to bottom, this is this, and it happens almost, I think, every digital system with some kind of computing capability, like computers or microcontrollers, even they have same kind of stages. So in the first step, when inputs are being checked, PLC takes a look at each input to determine if it's on or off. In other words, is the sensor connected to the first input on? How about the second input? How about the third? It records this data into the memory to be used during the next step. Then comes the execute program step. The PLC executes program one instruction at a time. Maybe the program says that if first the input is on, then it should turn on the first output, because it already knows which inputs are on off from the previous step. It will be able to decide whether the first output should be turned on based on the state of the first input. It will store the execution results to use later during the next step. And finally, we have the third step, which is the update output status. The PLC updates the status of the outputs. It updates the outputs based on which inputs were on during the first step, and the results of executing your program during the second step. Based on the example in the step 2, it would now turn on the first output. Okay, that's how the basic steps of the working of a PLC. And now we shall see some of how we can program a PLC. So normally we shall use ladder logic programming because it's easier and it's also commonly used. PLC programming is done with the help of special programming languages. The function of all programming languages is to allow the user to communicate with the programmable controller via a programming device. They all convey to the system by means of instructions a basic control plan. Ladder diagrams, function blocks, and the sequential function chart are the most common types of languages encountered in programmable controller system design. Ladder diagrams form the basic PC languages, while function blocks and the sequential function charting are categorized as high-level languages. The basic programmable controller languages consist of a set of instructions that will perform the most common type of control functions like relay replacement, timing, counting, sequencing, and logic. So these are some common type of control functions while you're doing programming a PLC. So what you're doing, you're turning on, you're checking some switches of the input, and then you're turning on some outputs, and there are some delays involved, some counting involved, or there is some kind of logic involved where you're checking, okay, if like AND operations or OR operations, if both inputs are on, then the motor should be on, something like this. We shall focus on ladder logic, as I already explained. So ladder logic is the main programming method used for PLCs. So this is a very common method. The ladder logic diagram has been found to be very convenient for shop personnel who are familiar with circuit diagrams, because it does not require them to learn an entirely new programming language. Modern PLCs can be programmed in ladder logic or in more traditional programming languages such as C. So you have multiple options. You can also program them in C language. This is also easy, I would say, C language. But since ladder logic is more like a visual language, easy to visualize, easy to conceptualize, easy to understand, so you don't need to learn actually some word-based languages, for example C language, which is difficult to understand as compared to ladder logic. The ladder diagram language is a symbolic instruction set that is used to create a programmable controller program. The aim of ladder diagram program is to control outputs based on input conditions. Ladder rung is used for the control. Control rung in general consists of a set of input conditions represented by relay contact type instructions and an output instructions at the end of the rung represented by the coil symbol. An example of ladder logic can be seen in figure below. So this is example here in this figure. This is the ladder diagram or ladder logic, and you can see you have some, these are inputs A, B, and then here you have output. Okay, sometimes they also represent it using output using like this sequence. Okay, so yeah, so this is output, X is output, A and B are the inputs, and then you have in the second step you have the C input switch and D. So this means this is the normally open switch and this is normally closed switch we have, and this is you have output. Okay, so how a program will read this how the PLC will read this program step by step. First it will read this step, and then once it's completed, this operation is completed, then it goes to the next line. In the second step it will read this. Actually the whole is the second step. So in the second step it will read all this here, and let's see in the what's details are written here. To interpret this diagram, imagine that the power is on the vertical line on the left hand side. Left hand side, we call this the hot rail. So this is the, it says that this one here, this is the power line. Okay, you say the power is coming from here because this language was designed based on relay logic. Okay, switch which are like a switches logic. So they assume that the power is coming from here. So let's say a battery is connected, and this is the positive side, and or this is the, you can say this is a neutral side, and here you have some voltages, and this is neutral, and then the power flows from here to here like this. So if this switch is, let's say, open, so the power cannot flow, the current cannot flow, and if when you close this switch, then the current can flow finally and turn on this motor. Let's say if there is a motor here, motor or alarm or bulb, anything. On the right hand side is the neutral rail. Okay, this side is the neutral, or you can also call it maybe negative, whatever you want to. You just have to make it similar to an electric circuit. Okay, in the figure there are two rungs, and on each rung there are combination of inputs, two vertical lines, and outputs, circles. If the inputs are opened or closed in the right combination, the power can flow from the hot rail through the inputs to the power outputs, and finally to the neutral rail. An input can come from a sensor, which switch, or any other type of sensor. An output will be some device outside the PLC that is switched on or off, such as lights or motors. In the top rung, the contacts are normally open and normally closed, which means if input A is on, and input B is off, then power will flow through the output and activate it. Any other combination of the input values will result in output X being off. So how this motor M or the output X will turn on? If your switch A is on, okay, so normally it's in the normal state it's off, but when you press it, it will on. So then it will become like you can say now it's on. The current is passing from here to here. And switch B, normally it's closed, but if you press this switch, it will open, so the current will not pass. So you have to let it close, let it be like in a normal state, and then current flows from here and turn on the motor. Okay, and in the next step you have, if you want to turn on your output Y, so what you have to do, you have to let the switch C in its normal state, turn on the D switch, okay, and also simultaneously you have to turn on the G switch. So once these two switches are on, the current will start flowing from here to here, and your motor will your output Y will be on. Let's say this is alarm A, alarm will be on. And meanwhile you also have some more inputs. For example, here you have switch E, switch F. Okay, so if switch E and F both are on and your switch G is on, or either your switch H is on, then your output Y will be again on. So this is like an OR combination. Either you have to turn on D, or you have to turn on E and F both at the same time. And other cases also, if from these two also, these are OR, they are connected in OR combination, and then G and H, they are also connected in OR combination. And these two, this section and this section, they are connected in AND combination. But in later we study in detail how we can make AND and OR combinations using the PLC, ladder logic programming. So just see quickly some application advantages and disadvantages of PLC. So the applications are, PLCs have now become very convenient tool for flexible automation. We have studied the flexible automation, and in flexible automation you can actually so you see that we used to have this fixed automation, and then we have programmable automation, and then we have flexible automation. And it's flexible because we said that the way we designed our automation system. Okay, so we have now studied that PLCs can help, actually PLC system can be flexible, quite flexible, because in a PLC system you can use components in different configurations. You can use this same button with motor 1 or even motor 2, or for alarm. So you can switch components configurations. Okay, so that's why it's flexible. On the other hand, if you have traditional systems where things are hardwired, the connections are fixed, it's not flexible. Maybe it's programmable, but it's not really flexible. Okay, and yeah, so this is one of the advantage of the PLC systems. The second is the applications of PLCs include, okay, control of electric motors in, okay, this was not the actually application, this was just okay. So the applications are the control of electric motors and industrial drives. In almost every industry you have some DC and AC motors, and sometimes there are also stepper motors nowadays, so you have to control them. Okay, and for that you need a very strong and you need a controller that's very that works in these harsh environments. So PLC is the best suited controller for that. And then you can use PLCs in your CNC machines, and then you can use them for robot control, because robot is also, it has motors in the joints and you have to control the motions. So PLC is best suited also for robot control. And in home and medical equipment, in home also, in home automation you can use either simple microcontrollers or you can also use actually PLC if you want more like professional looking and more stable system in home. For example, automatic garage door opening, or some other kind of, for example, temperature control or humidity control. So you can use this in your home applications. And then medical equipment, for example, you can use them in hospitals, in the some kind of machines, some scanning machine, for example X-ray machines, or maybe in the these MRI machines, so where you need different kind to control some actuators. And then you have applications lift in the buildings. So whenever you have to use the lift going up and down on different floors in the building, so there they can also be used, and they are mostly being used already in those type of environments also. And then you can use them in control of traffic light signals. So this is also, I think, most commonly used. Mostly the traffic light signals, they use already PLCs. And then safety control of presses. So in also some mechanical and material industries, you have these hydraulic presses where you press this hot iron or some steel sheets, and for there you need a lot of safety regarding how much pressure you need and how much force you're going to apply, and also maybe some temperature control, how much at what temperature the steel or any other material should be melted or heated. So all these control processes, PLC is best, I would say, best suited for these kind of processes, because their environment is very, very rough, temperatures are high, and if you use some kind of simple microcontroller or maybe computer, because they are not designed for these kind of environments, but PLC, they are designed for all these harsh environments. So we have all the applications here, and now let's see some advantages and disadvantages. There are significant advantages in using programmable logic controller rather than conventional relays, timers, counters, and other hardware elements. So what his comparison is between the conventional or traditional methods that were previously being used before PLC, these hardwired methods. So we are going to compare the conventional relay systems with the more flexible PLC systems, okay? And the advantages are: programming the PLC is easier than wiring the relay control panel. So your one option is you wire your circuit board using the relay and lot of other electrical and electronic equipments, and once you do that, then it's hardwired, okay? Because once you design your relay system, for example, this is your motherboard and hardboard, or you can say, and then you put there some relay here. This is relay, and this is, let's say, a capacitor, and then you have here some inductor, and then you have some resistors, and these are some outputs here. These are some inputs here. So once you have done this, then your circuit is really hard to change, okay? The only case is if you're using here breadboard, then it's easier to reconfigure, but normally it's not a case. Previously in the history, you always use some kind of like soldering the equipment, so they are very strong, they don't disconnect. On the other hand, if you use a PLC, using PLC, you can actually make connections very easily by just programming it, by just connecting the inputs and outputs to different systems. So that's the advantage of using the PLCs. It's highly reliable. It's reliable because it is designed for reliability, okay? It's designed for much higher range of temperatures, and for maybe some shock, higher shock handling ability. And then there is also some protections against different kind of maybe ripples in the electricity, okay? And then also overload, underload protection in case of things there is some accident. Then there are also some safety circuits inside the PLC that will help them to protect from damage. So a PLC, in short, it's a reliable device. Okay, the next is the PLC can be reprogrammed. Conventional controls must be rewired. okay, and are often scrapped instead. So I think we already discussed before, it can be reprogrammed, but the hardwire system, you cannot rewire them, you just have to throw them away once they are no more usable. And the next advantage is that PLCs take less floor space than relay control panels. This is also a very good advantage of PLC, because if you design a fixed controller using relays and some timers or other equipment, it will take a lot of space as compared to just a PLC. And since PLC actually is a multi-purpose flexible, so this also beats hardwire system in terms of, for example, a single PLC can perform like so many different kinds of operations, that to do same kind of operations using the hardware system, you need a lot of space. And next we have little maintenance due to no moving parts. So PLC is totally electronic, so you need actually very little maintenance there. The problem is usually when there is some moving parts and then you need to maybe lubricate them, okay, and they just create problem because of wear and tear friction, but in PLC this is not the case. And the next one is the no special programming skills required by maintenance personnel, because ladder logic is mostly it's easier to learn, it's a visual language, so you don't need actually special programming skills. Then we have the computing capabilities. So also it's not like in a hardwired system, fixed system of relays, and there actually you can build logic, but actually it's not really, the computing power is not really there. There is no computation there, okay? But in PLCs you have a microprocessor, and you can actually perform some computations like basic addition, not actually basic addition, you can like addition, multiplication, and these kind of computations you can perform. Reduced costs. This reduced cost is the overall cost reduction, because of once you invest in the PLCs, then you don't need to buy actually a lot of hardwired circuits, okay? And in the long run also, when you have to shift your to the flexible automation, actually it will reduce the cost, because you don't need to change the whole automation system, and this will actually, in the long run, it will reduce the cost. Then we have ability to withstand harsh environments, that we have already covered. Expandability, so you can expand the PLC system, you can connect multiple PLCs readily, because they have already these communication ports available where multiple PLCs can connect with each other and also with different other kinds of equipment. High speed of operation. This is, I would say, this is it depends upon what kind of PLC you buy, and maybe some older versions, they are not that high speed, but the newer ones with better and modern microprocessor, they are, of course, they will be perform tasks at a very high speed. And now let's see the disadvantages. Although the PLC systems have many advantages, there are also disadvantages. These include fault finding, as the PLC systems are often much more complex than the hardwired relay systems. So fault finding is difficult because microprocessor and all these microelectronics is so tiny that you cannot really repair or find a fault. If, let's say, microprocessor is damaged, then you cannot really say that, okay, where is the problem, and you cannot really repair it. You can replace it, but repairing it will be much more difficult. And then you have failure of the PLC may completely stop the control process, whereas a fault in a conventional control system would only disrupt the process. Okay, so this is again because the nature of the two circuits, the hardwired circuit and the if you have noticed that once the RAM of your computer is damaged, your computer will not work. Okay, it will not perform normally. So even a single component failure will result in the failure of the whole system. And same is true for microprocessor. And so if a PLC is damaged, something is damaged in a PLC, then your whole system will become damaged. It will not work. But on the other hand, if you are using these conventional hardwired relay circuits, if one relay is damaged, then the other portion, if they are not damaged, they will keep working. Okay. So this is a problem. Actually, this is a big problem because your whole system is dependent on a single PLC, and once it's gone, your whole system, automation system, will be stopped or it will become failed. And the next disadvantage is external electrical interference may disrupt the PLC memory. This should not happen often, I would say, but this may happen sometimes because sometimes there are some situations where there are a strong electrical interference and it may damage the ROM or even the RAM of the PLC. The damage can be temporary or it can be permanent also. So that's one of the problem. And because in the industry you are dealing with actually higher voltages, it's not like in the normal, for example, in the home, or let's say in the computer you're using just the low voltages, but in industry you are using sometimes high voltages because the motors are high power, and so it can disrupt. But generally speaking, it should be rare because the PLCs are designed in such a way to reduce the external influence. Okay, so these are some advantages and disadvantages we have studied, and now let us see what we can do more about ladder logic programming. Okay, so let's try to now see some examples of the ladder logic. And the first thing is, let's try to build AND circuit. And logic in ladder diagram. Okay, so in AND we normally use two switches, so we will write something like this, and then you have switch number A, and then you have switch B, and here you have output. Let's say this is a motor M, and then you complete the ladder. So this is an example of an AND circuit using the ladder diagram. And if you see why it's AND, because switch A is normally closed or normally open, sorry, and switch B is also normally open. And if these two are normally open, so it means that there is no way this motor will turn on. So the only way the motor will turn on if switch A is on and switch B is on, then motor M will turn on. So this is how this is the logic ladder diagram of for the PLC programming. And let's see about the OR, how we can program for the OR. For the OR, you have to just use same two switches, but this time you have to use them in parallel. This is switch A, which is normally open, and then you have the switch B, which is again normally open, and then you have here the motor M. So in this case, any one of the two switches, when they are on, then your motor will be on. Okay, so these both switches are normally open. This is also normally open, so motor M will turn on when either switch A is on or switch B is on. So any switch when it's on, motor will be on. In the other case, both switches, for the AND logic, both switches must be on to turn this motor on. Okay, now let's see if we want that we have a switch and we want to turn on the motor, but we want that it should always, once it's on, it should always stays on unless we stop it. So this is a case we have. So design a ladder logic diagram for a circuit such as when switch A is on, then motor M is on and it stays on till the switch B is pressed, is on or pressed. Okay, So this, we want that. This is a common scenario in the industry where you have one time you turn on the motor, it keeps running, and then later if you want to turn off, you press the stop button. Okay, so for that we need so first you need a switch A, and switch A should be normally open, because once you press this switch, the motor should turn on. Okay, and now what you have to do, you have to include another switch here in parallel to switch A, and this switch actually represents the state of the motor. So if the motor is on, this switch will be on. If the motor is off, this switch will be off. So normally it's off, and once the motor is on, this switch will be also on. So now let's see how it how it behaves, our circuit. So this is normally open, and this is normally open. So once we press this button, this switch, it will close and the current will pass and the motor will turn on. Once the motor is on, it will start running, and this switch also will turn on. Okay, and once this switch is on, then an alternate path is also created which runs the system, and the motor will now have two alternate paths. So if your switch A is a push button, let's say, this switch A is a push button, then if even you don't push it anymore, the motor will keep running through the alternate path from here. Okay, so once you push the button, this switch, the motor will turn on, and once it turn on, this state switch will be also on. Okay, and this is not like something like a physical switch, it's like an internal switch of the PLC that represent the state of the output, and once it's on, it will create an alternate path for the current, and motor will always keep running. So now to stop this motor, we need another switch, which is switch B. This is also push button switch, and for that we need to include here another switch which is normally closed switch. It's like this. So this is switch B, and this is normally closed. So normally the circuit is closed, the current can pass, but once you push this, okay, once you push this button, it will open. Okay, so when you want to stop previously the motor was running, and once you want to stop this motor, then what you need to do is to just push this button, and once you push this button, the circuit will open, and once the circuit is open, the motor will stop, and then the motor will stop, this state switch will also be open now. And even then, if you don't push this button anymore, the motor will not start again until you push this button again one more time to start this button. So A is actually the start button and B is the stop button. So this is the simplest circuit for this problem we have. And Let's take one more example. So let's assume we have a conveyor belt here. And this conveyor belt has a motor here. This is motor 1. Okay, and so here we have sensor A. Let's make it with some other color. So sensor A, this is attached here. So what this sensor does, it actually detects any object on the conveyor belt. Okay, so in this area it detects the presence of object. If the object is present on the conveyor belt or not. And then you have here, you have let's say a box here, and on this box you have sensor B. So sensor B, what it does, it detects the object when the object is in this box. Okay, so we have these two sensors, and this is our, we have one actuator which is motor 1, and we have two sensors, the inputs. Okay, and we have to program them such that I think we have to make them a little bit far, so we can assume that sensor A can actually detect the object in the whole conveyor belt, and sensor B is able to detect the object in this box. So you can imagine them as a proximity sensor or some kind of laser sensor or maybe a camera. So the main purpose is that it's able to detect the whole object. Okay. This is sensor A, and here we have sensor B. So this sensor A, it can detect object when it's on the conveyor belt, okay, and this sensor B, it can detect object when it's in this box. And this is, let's say, a box, and here we have, let's say, an object here. So as long as this object is on the conveyor belt, it's detected by sensor A, and when it reaches the box, it will be detected by sensor B. So our task is to design a ladder logic program that moves the conveyor belt as long as the object is present on conveyor belt. Once the object reach the box, the conveyor belt should stop. Okay, so we have to design a ladder logic program. So we need first this here, and then we have to here. So the first sensor is sensor A. Okay, we have to attach it like this, sensor A. So once the object is on the, once we place an object on the conveyor belt, then sensor A is on, otherwise it should stay off. So normally it's off, normally it's open. So we have to attach one normally open switch here, and we call it A, sensor A, okay, sensor A. And then you have to attach another sensor state switch which represents the state of sensor B. So normally if it should be, because the motor should be on when this sensor is even not giving any signal. So it means this sensor state, it should be represented by a normally closed switch. Okay, so even when there is no object, this motor should keep moving. So here we add a normally closed switch here, and then here you have a motor. Okay, we have only one motor, so we call it motor M. So this is our sensor B state, and this is normally closed. So what will happen, once you put object, this green color object, on the conveyor belt, it is detected by the sensor A, and what will happen when the sensor A is detects something, it will be on. It's like a push button, it will be on, and the current will start passing, it will this sensor B switch is already on. Okay, so the current will pass and motor will start moving. Once your object disappears from the conveyor belt, okay, and it fell down in the box, so this will be off. Okay, and your object will not be anymore on the conveyor belt, so this sensor will be off, and then your sensor B will also become activated, and this also be open. So in this case both the motor will then stop. So in the you can add one other line where you can add end here, and the program. So this is very simple program you can write here to operate this conveyor belt. Okay, so if this is clear, then I think we shall end our lecture here. So thank you very much for listening, and if you have any questions, you can contact me by email.